Welcome viewers. Welcome back to the video learning platform of Smart Coach India. Today in this video, I'll be teaching about the types of relation. So relations can be classified depending on the type of mapping and depending on the nature of the pair of elements present in it. So number one, classification is depending on type of mapping. So based on the type of mapping, relations can be classified as 1-1, number 1, 1-1 relation, number 2 is 1-many relation, number 3 is many-one relation, and number 4 is your many relation. So as the name goes, 1-1 means one single element is related to only one image. 1-many means one element may have more than one image. Many-one means many elements in the domain can have only one image, and many it goes accordingly. Clear? Now let us move to the second classification. As I said that the second classification is based on depending on nature of pair of elements. So depending on the nature of pair of elements, we can classify relations as number 1 reflexive, number 2 as symmetric, and number 3 as transitive. There is another special one, it is called the equivalence relation. So let us discuss them one by one. Number 1 is reflexive relation. So number 1 is your reflexive. So by the meaning of the word reflexive, we mean that if the reflection of the element is present in the set itself. Suppose let us consider, let R be a relation on any set capital A, let R be a relation on any set A such that the pair A comma A belongs to the relation R for all. This is the symbol for all. So for all A element belonging to the set A, then I will say that the relation R is reflexive. This implies R is reflexive because the reflection of the image is present in that relation itself. Clear? Number 2 is your symmetric. So again, let R be the same relation defined on the set A in such a way that if the pair A comma B belongs to R for some value of A and B belonging to the given set A. Remember, I am not saying for all, I am just saying for some A and B belonging to the set A, if there is a pair A comma B type in the relation R, this implies the reverse of this pair B comma A is also present in that relation itself, belongs to R, then R is symmetric. That means if I can reverse a pair and that pair is also a part of that relation, suppose 1 comma 2 is present in the relation R, then if 2 comma 1 is also present in that relation R, then I will say that the relation R is symmetric. Okay? The third one, that is transitive relation. Number 3 is your transitive. Now, for knowing what is transitive relation, let us consider two pair of elements. Okay? So, let the first pair be A comma B belongs to R and a second pair but starting with B, suppose B comma C again belongs to R, and what are A, B, C? There are obviously some values in the given set A, then this implies the set formed by the first and the last element, that means cancelling the middle common element B. If I get the pair as A comma not B, it is A comma C belongs to R, then R is transitive. This is C, remember. Okay? So, and what is equivalence? Equivalence means if a relation is reflexive, symmetric as well as it is transitive, then together it will be called as an equivalence relation. So, let us discuss a question for clarification of our understanding. So, the question goes like this. Question: let R be a relation defined on the set of natural number n as R equal to x comma y, any general pair in the relation R, such that it follows this guiding equation x square minus 4xy plus 3y square equal to 0, where both x and y belongs to the set of natural numbers. Then I have to determine what is the nature of that relation R. So, solution: if I solve this guiding equation, then if I solve this guiding equation, then I will get the factors as x minus 3y into x minus y equal to 0. Therefore, either x will be equal to 3y or x will be equal to y. So, these are the two component equations that we will be getting for the relation R. Okay? Now, number 1, let us check its reflexiveness, whether it is reflexive or not. Now, if I go by the second relation, that is x equal to y, so for x equal to y implies x comma x will obviously be a pair of element that will be present in the relation R. That means the reflection of each and every element will be in the domain will be a part of the relation R. So, therefore, R is what? R is reflexive. Number 2, we have to check its symmetricity. So, whether it is symmetric or not. So, now to check the symmetricity, I will be considering the first equation, that is for x equal to 3y, let us take some arbitrary pair. Suppose if I put y as 1, then I will get x as 3. So, this implies if I put y as 1, then I will get x as 3. That means 3 comma 1 will be a pair that will belong to the relation R. Now, let us check whether the reverse of this pair is also present in that R or not. That means 1 comma 3. So, you can easily use your rough work and you can cross check. If you have to check whether 1 comma 3 belongs to R or not. So, if you put y equal to 3 over here, then you will get x as 9. So, you will get 9 comma not 9 comma 3. If you put y as equal to 1 or 3, then you will get 9. Okay. So, but that means 1 comma 3 does not belongs to the relation R. That means the reverse of the pair is not available in the relation. So, therefore, R is not symmetric. So, therefore, R is not symmetric. Now, the last one is your transitiveness. Transitivity. So, for this I will take two pairs, as I have already discussed in the theory. So, you can yourself verify that 9 comma 3 belongs to R and 3 comma 1 also belongs to R, because these two pair of elements will be satisfying the equation x equal to 3y. So, they are obviously belonging to the relation R, but if you use your rough work and you see, then you will find but 9 comma 1 does not belongs to R. That means the set formed by the outer two elements does not belongs to R, therefore, R is not transitive. Therefore, R is not transitive. So, what can we conclude? That the given relation R is reflexive, but it is neither symmetric nor transitive. So, that is all for this video. Stay tuned. Thank you.